Hey everyone, how goes it? Welcome back to Computer Science 552, Game Development. Today, we're going to continue our discussion about game development. In the past lectures, we focused on concepts and roles related to game production. We also began discussing game development in a previous lecture. Today, we continue this discussion. We turn our attention once again to the role of the programmer. We focus on the element related to creating software in order to make a game. Our focus again is going to be on game programming. In a previous lecture, we discussed some of the values and concepts related to software engineering. Creating a video game is an exercise in software engineering. Software development processes help to plan, manage the tasks that are required to create software. A software pattern is a general, reusable solution to commonly occurring problems within the context of software design. As mentioned, some common software pattern categories are structure, behavior, creator, and concurrency patterns. In a previous lecture, we focused particularly on a behavior pattern commonly used in game software called the game loop pattern. The game loop pattern helps organize the game's behaviors into common occurrences. Each game loop iteration progresses the game. The event step involves gathering information about occurrences that have happened since the last game loop iteration and then applying necessary actions related to those events. User input, collision detection, message handling are common events. The update step modifies data periodically based on previous events and previous data. Moving the player, destroying an asteroid, collecting a coin, are tasks that are commonly performed during the update step. And finally, the draw step displays the results of the update. In games, a frame is an abstract unit of time between the game loop iteration. Typically, one game loop iteration is equal to one frame, which is equal to one turn sequence iteration. Each frame progresses the game. Real-time games mean that the frame progressions match closely to actual time. Sports, real-time strategies, platformers are examples of real-time games. Turn-based games means that the frame progresses only when certain criteria are met. RPGs, chess are examples of turn-based games. There are steps that exist outside the game loop that we also need to consider. The initialization step is when all the data for the game is created and set to default values. This occurs before the game loop. The finalization step is when all the data is deallocated from our memory, and this happens after the game loop. For argument's sake, the initialization and finalization are not part of the loop, but are considered elements of the game loop pattern. However, when we decide to create games that involve much more features, then we need to consider more sophisticated structures and patterns. We consider more game features require more sophisticated structural organization. Video game or game software is the collection of all the game-specific code, libraries, systems, and engines that compose a game. The game system is the code which runs or drives the game. It is in charge of calling the functions related to the game loop pattern, contains software libraries used to write the game-specific code, and this is all considered to be separate from the game-specific code itself. A game engine provides many of the features common in most modern games. We do not need a game engine to make a game, but as a developer, it definitely speeds up the process. Game-specific code is the software specifically developed to create a game. This again is separate from the game system and the game engine, and it typically uses provided features and programming interfaces that is provided by the game system or game engine. A game engine is a software framework for developing games. This includes necessary software libraries and supporting systems. Commonly, it contains the graphics libraries, physics engine, input managers, audio managers, and message passing capabilities. Game engines are not required for making games, but they do speed up development time. In most cases, the game engine can be considered the game system. They both contain the necessary software libraries in order to create a game, and they are both in charge of executing the game loop pattern. Now, as previously mentioned, there are some non-typical games that may require additional software. So, the game system is just a larger concept, but a game engine can be considered to be the same thing. Understanding this, we now need to address how software can be better structured for our games. Game software structure can be viewed in a slightly different way than most typical object-oriented design software. Entity Component Systems, ECS, puts more stress on the composition over inheritance. It focuses on not what it is, but what it does. This relates heavily to the concepts of the observer pattern or mediator pattern. The component pattern allows a single thing or behavior to span multiple domains without requiring specific relationships to another. This is considered to be a decoupling pattern. It is much more in common with the composite pattern, where programming objects are composed of other programming objects. Component-based development emphasizes the separation of specific functionality with respect to the wide-ranging functionality available throughout a given software system. Components for games are classes of behaviors. We create classes of behaviors instead of classes of things. This is opposed to hard-coding functions or methods within a large monolithic class. This means writing everything in one programming file or just writing all the code in a main method. The code for components are based on the game loop pattern. Separate functions exist for initialization, events, update, draw, and finalization. Typically, within a game engine, there is a component programming interface for which all components inherit or implement. Game objects are the abstract nouns in a game. Every thing in a game is a game object. Every object, every player, every enemy, every rock, everything in a game is a game object. Game objects are considered to be entities in relation to the entity component design. They are simple containers for components. In many cases, game objects can be considered to be the same as components themselves. Generally, classes are not specifically created for different game objects. In other words, there is no class written for player, for enemy, for exploding barrel, or heads-up display. Game engines commonly use a game object type, a data type, which is used to extend into other specific game objects. Game objects are different based on what behaviors they perform. Again, the difference is not in their data type, but what they do. By using this structure, this allows for functionality to be abstracted. Many game objects perform the same actions so that we may share the same components. We can see both player and enemy move and draw. We consider writing one class move and another class draw and simply just adding those to the player and enemy game object. The component's attributes may be different in each instance, but the component does the exact same thing. A player's speed and an enemy's speed may be different, but they still move the same way. From a functional standpoint, they do the same action, but with different values. Game objects may swap in and out different behaviors. The flexibility of being able to decouple this can allow some game objects to either gain or even lose abilities. Writing game code requires understanding what are the nouns, the things, and what are the verbs, the actions and behaviors that are inside the game. One way we can start doing this is by noticing the nouns and the verbs when reading through the game design document. By categorizing nouns and verbs, this assists in writing the technical design document. Game code is generally composed of game objects, the nouns or the things, components, the verbs, actions, and behaviors. This becomes the foundational structure of games. When we are designing games, it may be useful to draw out the concepts so that ourselves and especially others may understand how to create the game. In software engineering, we are aware of a unified markup language or UML diagrams which help us design software. A component diagram is another UML diagram which demonstrates how components are connected, forming a larger system. It is a specialized version demonstrating provided and required programming interfaces. Keep in mind, programming interfaces are not the same as user interfaces. Components are typically drawn with a box with its identifier. The phrase component is also typically placed in the box as well. It may also have an icon composed of a larger rectangle with two smaller rectangles centered to one of the edges. It may be clear that component diagrams can be created in a variety of ways. Components connect to each other using programming interfaces. We keep in mind that programming interfaces are not the same as user interfaces. These instead create rules for other programmers by establishing expected functions or operations that are to be implemented. Through these connections, the components communicate with each other. One way that we model this is using a ball and socket connector. The ball represents the component and provides the information or functionality. The socket represents what the component requires, and again, this is for information or functionality. Above context helps provide either the symbol to better describe the relationship. This helps us better understand what it needs and what it provides. We once again keep in mind that component diagrams can be created in a variety of different ways. These relationships can be drawn from component to component or from game object to component. Game objects require specific behaviors to be provided. This can begin to get messy very quickly as the game object is more or less just a container in concept. We may consider designing it this way. We understand that components may be composed of other components. As mentioned before, game objects and components are composed of other components. These internal components can be demonstrated by enclosing them inside of a larger component. With large systems like games, this can create a better understanding of how the actions can be grouped into these structures. For a game code design, it is useful to further differentiate a game object and a component. We can use GO to represent the game object and component to represent behaviors. Using this, we can establish what the game object needs to do by enclosing them within the game object structure. The internal components then are connected together using the game object. The internal components are then connected together to create the game object. Typically, we focus on implementing the game code through the components and provided interfaces. The game objects and their components are smaller parts of an overall game system. In game design, we discussed how all games are systems. Commonly, the game system is the code which runs or drives the game. It is in charge of calling the functions that relate to the game loop pattern. These function calls can be considered event messages that are sent to each game object and then delegated to each component. We notice a new type of connection between the ball connectors. This is a slightly different kind of relationship that is not as strong as the connection between a ball and a socket. In that type of relationship, the socket implies a very strong dependent relationship and must be provided by another component. However, between ball connectors, the relationship means that they are not as strong. This is why we denote it using a different connector using a dashed line instead of a solid line. This may seem like a strange kind of relationship, but consider that these kinds of connections relate heavily to the concept of event messages. These are broadcast from a source, acquired from a receiver, and then delegated to related components. We consider that the source provides the message, and the components provide receivers to listen. As this kind of system focuses primarily on broadcasting messages to corresponding components, we know this is based on the concept related to the observer software pattern. This software behavior pattern creates a one-to-many dependency, so that the state of one object, when it changes, the dependent objects are then notified about it. This is great as one message can be delegated to any number of components. For instance, init, events, update, draw, and final can be broadcast from the game system to each game object. Then each game object delegates these messages to each component to handle its steps separately and differently. This implements the game loop pattern. In addition to the game loop pattern, the game system also is composed of libraries and other systems and programming interfaces. It provides the game developer with features commonly found in games, and can be considered to be the game engine in most cases. As we've mentioned, the dashed lines represent delegation of the required actions to provide functions within each component. Delegation meaning delivering an event message. This is an event message that is broadcast to all the components within a game object. One event may have code handling it in several different components. The components handling these events can be considered to be listening for these messages. This delegation is used so that one event message may be handled by any number of components. The same event may be handled differently by many components. So for instance, getting hit by an enemy's attack both will reduce the health and knock the player backwards. This one collision event will be handled by the health system and a move component separately. A larger example of this is an update may be different from one component to another component, but they still need to be updated. Consider in a 3D game first-person move component that is going to be slightly different from a look-around component. These two actions both update the player, but moving and looking are two different things. We can create these diagrams in a variety of ways, but the purpose of creating the diagram is not for creating the diagram. It's to communicate an idea to others so that they may implement your ideas. As components commonly implement programming interfaces, these functions are assumed to be written in the component's code. As mentioned, the programming interface for a game component typically has the functions representing the parts of the game loop pattern. These once again are init, events, update, draw, and final. Keeping all these common messages in the diagram makes the design a little messy. So there are some common assumptions that are made for the sake of cleaner diagrams. The game system is composed of a collection of components that are called game objects. Game objects are composed of behaviors called components. The game system follows the game loop pattern, initializes each game object and each component within, handles the events for each game object and for each component within, updates each game object and for each component within, draws each game object and for each component within, finalizes each game object and for each component within. With this understanding, we typically omit these event messages and delegations because they're always assumed. However, unique event messages and their delegations are still represented by that dashed line. These are generally many game-specific events that relate, and they should be diagrammed. When creating the technical design document, it is important to have details regarding the game object and components. For each game object, provide its name, a description, and the required components, which is just a list of behaviors that are assigned to the game object. There will be some more details when discussing advanced structures such as tags, categories, children and related game objects, or whether or not the game object is a prefab or is it unique. For each component in the technical design document, we provide the critical information regarding its functionality. This includes its name, a description, provides, in other words the data or functionality, requires, data and functionality, and some extra internal data. We keep in mind that these are considered high-level descriptions of the behavior, and they are not concerned with the strict implementation of them. In other words, in this type of description, you would not go into the detail of saying that you need this type of variable to be an unsigned 32-bit float. No. We have to leave it up to the programmers implementing or writing the software to interpret this themselves. We take the information from the technical design document and start implementing the components. The designs in the technical design document are not overly detailed and leaves interpretation to the programmers. With our knowledge of structure and behavior of these components, we can now more thoughtfully start writing the code. With this knowledge and our own development experiences, we can understand that components only need to implement functions specific to its purpose. not every function needs to be overridden. When writing the code, we consider that each one of the steps are part of the game loop pattern and what it addresses. Initialization is what happens when it starts. How is the data initially set? Events. What messages are we listening for? Update. How does the data change? Draw. How do we display the change? Finalization. What happens when it's destroyed? In fact, components may only need to implement only one of the game loop functions. For technical design documents, game object and component diagrams are preferred over other types of structural diagrams. We know that there are many types of diagrams in software engineering. Creating a component diagram then demonstrates how to put it together, while also leaving some interpretation for the programmers. Alternatively, creating a UML class diagram shows how the code is constructed. We're not going over creating a UML class diagram, as more often than not, it doesn't serve any useful purpose for making a game. Now, let's take a look at this structure using a previously developed game concept. Once again, we're going to look at our high-low game. We must implement the high-low game from a previously designed game concept. Reviewing this again. High-low is a classic puzzle game where players must guess the correct value randomly picked with only a few guesses. The materials we have is a player and a referee. The setup is the referee selects a random value from a known set of values. So for instance, let's assume 1 to 100. The referee knows the player only has a fixed number of guesses. For example, let's assume that the maximum guess count is 3. Finally, the referee sets the player's guess count to 0. The turn sequence is, Step 1. The referee informs the player that they have selected a secret number from a given number range and they only have a few chances to guess it correctly. Step 2. The player then guesses a value. Step 3. The referee increases the player's guess count by 1. Step 4. The referee then tells the player that their guess was either higher, lower, or equal to the secret number. Step 5. If the player guessed correctly, then the referee informs the player that they have won and the game ends. Step 6. Otherwise, if the player guessed either higher or lower but is still within the guess count, they repeat from Step 2. Step 7. If the guess count exceeded the maximum number of guesses, then the referee informs the player that they lost. The player wins when they guess the secret value within a fixed number of tries, but otherwise, they lose. First, we can immediately identify the game objects that are listed in the materials section. Both the player and the referee are the only two game objects in our system. This is a good time to note that the referee acts as a game's official. The game manager may appear in many different forms in the future, but the concept is still the same. Now, we can start seeing the components as the actions related. First, we see within the setup that these are the behaviors required to occur during the initialization step. We keep in mind that the structure is following the game loop pattern. We see this continued in this turn sequence. Each of these steps have been grouped together into a behavior that follows the steps events, update, and draw. Think about how these are grouped together and how we can start understanding the main actions seem to be related. Picking a secret number, making a guess, handling the guess. We can now start to see the actions assigned to their respective game object. The referee picks a secret number and handles the guess from the player. The player only guesses values that are sent to the referee. We can see how each of these actions are interconnected, and we can also remember the game loop pattern applies. We can see this is turn-based in nature and how the components call each other. Note that we omitted the game system as it assumed that we are making a game. While this is a good starting place, I must admit that this implementation for the game feels a little bit over-engineered. We've already demonstrated how to meet all the requirements for this kind of game, and we don't need this type of structure. However, it's good practice to start simple and work our way up to more complex designs. For each one of these components, this is how we would write about them in a technical design document, but also how we would implement them inside the code. The left side represents what would be found in the design document, and it details what the component does without being too specific. To the right is how we would implement it. we consider the component works within the game system and follows the game loop pattern. We can then organize the code within the pattern by acknowledging what it does and what it does during each one of the steps. Again, on the left that we see the component design. The name of this component is pick a secret number. This selects a secret number from a fixed range and then tells the player to guess a value. We can see how this would appear for handling a guess. Again, the left-hand side would be the design, the right-hand side would be implementation details involving the game loop pattern. Finally, we can also see this with guessing a number. On the left-hand side is the design, the right-hand side is the implementation with regards of the game loop pattern. Now with this in mind, let's take a look at a more advanced game and how this can be structured. This one is going to be very different from the last example as it's not turn-based, but it is real-time and features interactive movement. However, this can still be designed effectively using the game object component design using the game loop pattern. Our problem is to create a game called Table Tennis for Two. Let's first establish some requirements. Two players must be able to control two different paddles simultaneously. The player may only move their paddle up and down. A ball starts in the center of the board of each round initially. When one of the players chooses to start the game, the ball chooses a random direction and fixed speed and starts moving. The ball must be able to bounce off the player's paddles and boundaries of the screen. When the ball bounces off of a wall, it must be reflected 90 degrees from its incoming direction. When the ball bounces off the player's paddle, its reflection is based on the center point of the paddle and the collision point. When the ball collides with either of the player's goals, then the other player scores a point, and the game resets to the next round. A referee keeps track of the score, and the first player to receive 10 points is declared the winner. We can start seeing the game objects when observing the nouns in the requirements. We see two players, a ball, and the environment as being the walls and the goal. Finally, we also see the game official or manager called the referee. We can start seeing components by noticing the verbs. Focusing on what was related to the player first, we notice that the actions can be related to very simple concepts. User input is needed to access the controls and apply them to the paddle. Position, rotation, and scale is considered a special kind of component called the transformation or transform. We will go into a lot of detail about the importance of this component in future lectures. We also assume that we need collision detection, which is typically handled by a component called a collider. For now, let's just assume that it's a simple geometry like a circle, a box, that will detect collision between another collider. We can see one way to draw this component diagram showing how each of the geos share these components. We can also view this in a slightly different way, which shows the interconnection of each component. Both ways to draw this is valid, but typically it's more useful to show this and the interconnections within the subsystems of a game object. We also notice that there is an event message and delegation that is broadcast from the collider to the user input. Event messages may happen internally as well. We also notice that both of these are the same, and so we may consider creating one game object that can be replicated many times over. This is called prefabricated or prefab game objects, where we create it once and then replicate it many times over again. This is the exact same concept as creating programming classes that we use to create instances that we call objects. We can reduce complication of the design by using one instance and noting that it's a prefab in the technical design document. Now we can see the same thing for the game object ball. And we can see its component diagram here, demonstrating the interconnections. Now we can see the referee. Notice, we have called the component Scene Manager. This is a commonly used concept that represents the role of the game official, otherwise known as the referee. The key idea is this role enforces the constitutive and some of the operational rules of a game. We can see the referee simply diagrammed here. In this case, we note that it receives event messages and is diagrammed on the game object, as it's important to note that it increases points. This is a message that is to be handled by the Scene Manager script. We commonly omit receive event messages as we assume that they are provided by the game objects. However, this one is important to show how it's used. We can see that the goal game object requires the referee to send a message increase points. This then is delegated and handled by the referee's scene manager component. Now we can start putting it all together to see the big picture. We know that these game objects are within the game system, which is in charge of executing the game loop. More details regarding each component and game object can be found in accompanying notes. We notice that there's a few game objects that were mentioned to be prefabs, so let's take a look at an alternate version. If we assume player, goal, walls are all prefabs, then we can simply design this. A big takeaway is there are many ways to design games, and there's many ways to draw these diagrams. The main goal is to communicate the game's features and how to create it. We should focus on creating a game and not just creating designs to create a game. In this lecture, we've demonstrated the ideas related to the structure of game code by introducing and demonstrating the game object and component pattern. This structure is fundamental when understanding how to create games and will be explored throughout the rest of this course. And with all that being said, I'll see you next time.